Welcome to the Mental Exercises series. There are certain engineering problems that require calculus to solve, but in some cases, the problem only needs to be solved once. This is the case for the root mean squared value of a sinusoid. Even a novice of electronics will probably know this. The RMS of a sinusoid is the peak voltage divided by the square root of 2. We will derive that with calculus. Think of this video as mental floss to the brain. It may also help to reinforce your modesty, since there was a lot accomplished before you were born. Here's a sinusoid with a positive peak value and a negative peak value. Here's the equation for a continuous sinusoid waveform. We can substitute the angular frequency omega for 2 pi f, and we can substitute the phase angle theta for omega t. Here's the definition of root mean squared. For alternating electric current, RMS is equal to the value of the constant direct current that would produce the same power dissipation in a resistive load. The light bulb doesn't care if the voltage is negative or positive. Let's look at the relative area of the sinusoid to its peak value. It has a positive peak value and a negative peak value. Consider the positive peak voltage to be +1 and the negative peak voltage to be -1. Here's the area for the peak voltage, and here's the area for the sinusoid. The ratio of the sinusoid area to the peak voltage is 1 over the square root of 2, or 0.707. Now let's go derive it. As you may know from watching my other videos, I made a pledge: no math steps left behind. Let's look at the general formula for the root mean squared of any number of values x1 through xn. Squaring each value turns negative values into positive values. Each of the squared values are summed and then divided by the number of values. Since the act of squaring the values changes its scale, taking the square root scales it back to the original. Now let's look at a periodic function. You might think that doing an average would do the trick. But the sinusoid has positive values that are the same magnitude as its negative values, so they cancel, and the average is 0. Squaring the function turns the negative values into positive values. It's then divided by the period to get the mean, and then the square root to scale the number back to what it would be without squaring. Here's the general equation for the RMS of a periodic function. It's the integral of u of t squared dt from 0 to the period t, divided by the period t. Consider the case for the sinusoid. It's the peak voltage times the sine of theta squared d omega. It's integrated across the whole period from 0 to 2 pi, then divided by 2 pi. Before we go do the integral, we can do a lot to simplify this expression. We will make Vp its own squared term. Since it's a constant, we can move it out in front of the integral and then move it out of the radical. Let us first just work on the integral part. I'll call it A. Here's the integral for sine squared x dx. That's pretty nasty and will take a lot of effort to integrate. We can instead use our friend, the power reduction trigonometric identity. Sine squared of theta equals 1 minus cosine 2 theta over 2. Substituting that in place of the sine squared of theta, we can move the constant 2 out in front of the integral. Then we can use the integral sum rule to break each part into its own integral. Integrating the constant 1 from 0 to 2 pi is easy and is 2 pi. I'll plug the 2 pi in the left side of the equation. Now let's work on the right-hand side. For this, we can do a u substitution. We'll set u to 2 theta. Take the derivative and rearrange to be equal to d theta. Then substitute it in place of d theta. Since it's a definite integral, we need to adjust the boundaries to be relative to u. With theta at 2 pi, u is 4 pi, and when theta is 0, u is 0. Here's the integral with the boundaries changed to be relative to u. Now we can move the constant 2 out in front of the integral. The integral of cosine of u is the sine of u, integrating from 0 to 4 pi. Due to the periodicity of the sine function, the sine of 4 pi is 0, and of course the sine of 0 is 0. All this work, and the right-hand side goes to 0. Plugging these values into the equation we had for a gives us this. The 2's cancel, and a is equal to pi. Recall our equation for VRMS, replacing the integral part we call a, which is pi. The pi's cancel, and the RMS voltage is the peak voltage divided by the square root of 2, or 0.707. Because the sinusoid function has bilateral symmetry, we could have just integrated the sine function over a quarter of it, or pi over 2. Let's quickly repeat the calculus for the quarter sine wave. And lo and behold, we get the same answer. While this concept of root mean squared voltage is fundamental to engineers, I bet your friends and family would be very surprised if you told them the nominal voltage in your home receptacle is 339 volts peak to peak. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.